Hey guys! Alright, so today we're going to be talking about some reflexes of the body. Reflexes that go from a muscle or a tendon or some sensory nerves in just anything. And then those nerves, whichever ones are triggered of those three, go to the spinal cord and then immediately have a reflex happen without any interaction to the brain. And so that's why reflexes can be so fast. All right, so we're going to go over those three and hopefully make sense. So first, to give kind of an overview of why I wanted to talk about each of them, and then we're going to go into details. So the three reflexes are stretch, also known as myotatic reflex. That's one. The next one is inverse myotatic. And then the last one is like the pain reflex or the crossed extension reflex, okay? So stretch reflex, what is it? Why does it happen? So stretch reflex, if you think about any muscle, take the biceps, okay? So if the bicep is going to be torn off because, let's say, a dog bit me right here and was about to tear it off. Obviously, my body doesn't want that to happen. And so we have receptors, we have muscle fibers called spindle cells, and they are mechanoreceptors, meaning that when something mechanically pokes them, physically pokes them, they send off some signals. And so when it says, whoa, we're being stretched, stretch reflex, we need to stop this muscle from being torn off. Then they're going to trigger the muscle on this side to contract, which makes all the sarcomeres, if you remember the sarcomeres and all the myosin heads and the actin filaments and how contraction brings those together and they all grab each other, it makes sense that when those are grabbing each other, it's a lot harder to tear the muscle when you have all these really strong bonds between firm threads, firm fibers, myosin and actin, times thousands of myosin and actin in each muscle holding on to each other. So the stretch reflex is making so that the muscle contracts, so it is much harder to tear that muscle. So, and if this side contracts, we certainly don't want this side stopping that. And so this side relaxes. Okay? So the stretch reflex, that's the same with the knee. If you hit your tendon here, then that makes this muscle here, your quadriceps, contract, and it makes your hamstrings relax, okay? And that's because that muscle feels that it's getting stretched, and so it's like, oh, better contract so we don't get stretched so much we tear. Okay, second reflex, the inverse myotatic. All right, the inverse myotatic is when you're actually contracting super hard, okay? And we have a tendon at the end of virtually every muscle, most of them. And if that tendon, which happens to have something called the Golgi tendon organ in it, that Golgi tendon organ can say, whoa, this tendon's about to tear, that's really bad, we need that tendon not to tear. What's the best way to take the pressure off that tendon? It's to make that muscle relax. You're picking up something too heavy, the tendon's about to tear even though the muscle's okay, and so it's saying, relax. Now, if this side needs to relax, the opposite of the previous reflex, you'll notice, then this side is going to contract to make sure that that happens as effectively as possible without them trying to do opposite things. So, inverse myotatic is to save the tendons, has the Golgi tendon organ as the mediating response, the one that can tell, whoa, we need to drop this, and it has relaxation and flexion, okay? The third response is the pain reflex or the crossed extension reflex. Okay, so I'm going to see if this can work here really quick. So, can you see the floor? Okay, so if I step on a Lego, it's going to hurt. Now, it makes sense that I would immediately take my foot off, right? Which means that I now flex on the side that the pain was from, and I would relax back here. I'd relax here. But let me show you what it would look like if that was the only thing that happened. Because while I'm walking, this other leg was just about to take a step. So it would look like this. I would step, I would go, ow, which means that this would flex, and then I would come down like this and fall because both my knees were in a flexed position. this leg was just in the act of flexing to take the next step. And so if they both flex, I'll just go down. So that means we need to have not only this leg say, come off the Lego, flex on the front and relax on the back, but we also need this leg to extend to keep me from falling and to keep my balance. Okay, so that is called the crossed, that's why it's called the crossed extension reflex. Because while the first leg flexes, the other one extends. All right? So if you know that, then you can figure out where all of the motor nerves that we're going to talk about in a second are going to go, which is why I wanted to talk about it as an idea first before we get into the nitty-gritty. Okay? One other example of the cross-extension reflex that our professor gave us in class was when he had Cody come up and he grabbed one of Cody's arms without Cody knowing exactly what he's going to do, and Cody's other arm did the opposite thing a little bit. So you can remember, if one goes one way, then the other one's, it's an opposite reaction, which has to do both with balance and with the legs from keeping you from, falling. So let's begin with some details. All right, so this is actually kind of fun. So myotatic stretch reflex. There are three kind of categories here that I found helpful to know. You can ignore that if you don't like it. We'll be going down here to this diagram a little bit to go through each of them. So the first things, if you can remember on and off, on with the flexor, off with the extensor, and remember why that is. You're trying to save that muscle that's being torn off, and so you want it to, the affected muscle to contract, to save it from being torn. If you can remember why, then obviously this is the one that turns on, this is the one that turns off, okay? And next, before we go down here, I want to cover spindle cells, okay? Every muscle has spindle cells in it. And those spindle cells are the detectors of the state of the muscle. They can tell if the muscle is being contracted. They can tell if it's being stretched without us contracting it, so that would be if something outside is doing it. And they can tell exactly how, what state it's in as well. Not just if it's being contracted, but like what angle, how short is it, okay? So these spindle cells are, well, they're spindle shaped. And it just so happens that the word fusel means spindle shaped. So if they're inside the spindle, if some fibers are spindle fibers, they will be called intrafusal fibers, okay? Inside the spindle fibers. They're muscle fibers just like the rest of it, they just have some special jobs, okay? The rest of the muscle would be called extrafusal muscle fibers, all the rest of the muscle, okay? So, moving on, inside the spindle, the intrafusal fibers have a couple different types of intrafusal cells. There are chain cells, and conveniently, the nuclei in the chain cell are, well, they look kind of like a chain. They are one on top of another, and they look like a chain, and so they got named chain cells by looking at the nuclei in them. There's also bag cells, which is another type of intrafusal cell. Bag cells are characterized by a clump of nuclei all together, kind of like a bag full of marbles, if you will, okay? And so those two help each other to give two specific responses, two specific reporting responses. So the spindle cell, it has, with these two cells, it is able to, number one, tell if there is an external change to the muscle, and these are mechanoreceptors. Mechanoreceptors respond to mechanical touch. And so if that happens, they're able to send a signal saying, the muscle has changed and you didn't do it, therefore you need to contract. And they send a ton of action potentials to make the contraction happen. And that's the reflex side. There's one other thing that they do. There's also just constant reporting, okay, coming from the spindle cell. All right, so right here you see that there are two two sensory motor nerves coming out of the spindle cell. All right. One of them represents, well, both of them represent sensory information coming, and they will act on motor nerves that I'm going to draw here in a second. The second thing that they do, besides the motor nerves that save the muscle, they also have a little bit of information that actually just gets sent up to the brain via a pathway that we don't need to know more about except that it exists. And that information is just how long is the muscle? What does it look like right now? Why do we need that information? Why do we need to know that the muscle's here or here or here or here? Well, if you stop and think about it for a second, why don't you close your eyes, okay? Close your eyes. Now, put one of your hands out at a weird sort of angle. Just raise your hand in a weird way. Okay, now without opening your eyes, take your other hand and grab your wrist of the raised hand, all right? Now open your eyes. Why were you able to find your wrist so easily? It's because of proprioception. Proprioception is your body's awareness of where all of its appendages are oriented in space. So you didn't have visual data to guide your hand, so you had to go off of proprioceptive data. Proprioceptive data is your body knows that this muscle is this contracted, and it knows that this forearm wad of muscles are this much contracted, and it knows that your wrist was contracted on the ulnar side and the radial side was extended, and by all of that it can calculate all the angles of where your hand should be, and so then it is able to guide the other hand and just grab it and know where it is oriented in space. That is called proprioception. If you didn't have that and you closed your eyes and tried to grab your other wrist, it would be very difficult. You'd probably end up doing something like, okay, well, here's my shoulder, let's follow it up. Kind of like if someone else was holding their hand in space. Okay? So, that is the other kind of information that comes from spindle cells. All right, so now let's go into the motor nerves really quick. So, sensory nerves go to the spinal cord. Some of them report to the brain with just that proprioceptive data. And they also, besides the reporting for the proprioceptive data, they also will trigger that stretch reflex will trigger contraction, okay? So, now obviously the contraction, you will want to be on the muscle that's being overly stretched. And so we're going to call it the flexor in this case because it's the one that's going to be flexing. And to inhibit the other one, obviously you want the inhibitory signal to go to the extensor, okay? And so we're going to put a little negative here because it's inhibiting. We're going to put a positive here because it's an excitatory postsynaptic potential. It's causing flexion. Now, this mess of motor neurons on the board is, if you know which one is supposed to be flexed, then it's easy to draw it out. And that's why we started by saying this one flexes, this one extends, because that is literally all those neurons are saying. Okay? There are interneurons that we'll talk about a little bit really quick. So from the spindle cell, we have sensory neurons that go to the spinal cord. That's what this is. Spinal cord posterior is back here, which is where sensory neurons come in. Anterior is this side, which was where motor neurons come out. Interneurons are in between all of these reflexes. Interneurons are just short little neurons that the sensory ones talk to, and then the short little interneurons talk to the motor neurons. The reason for that is kind of complicated, but I might get to that in the end if this doesn't get too long, because I know long videos aren't what you're looking for. So, all of these reflexes use interneurons. There's only one exception, which is really nice. So you remember the one exception, and you know that the rest have interneurons. The only thing that doesn't have an interneuron is in the stretch or myotatic reflex, the one we're talking about right now. The signal to the flexor, the one that's supposed to flex, there is no interneuron. Okay? The sensory nerve talks directly to the motor nerve. All right. So now we've covered what turns on, what turns off, and the motor neurons. We've also covered the spindle cells and the three things that you want to know about them. Intra and extrafusal, why are they called that? We covered that. Chain and bag cells, we covered that. So cell types. And then what do the mechanoreceptors do, which is the third thing, and that's reporting as well as stimulating contraction to save the muscle. And so they send out, if they detect a change in the muscle that was extrinsic to you, so a dog is biting on it, someone grabs it and pulls it, what have you. That's the other thing that they detect, is a change in length that you didn't do. Reporting current length, reporting changes in length that you didn't do. Okay? All right, and the reporting of the change in length is the one that stimulates contraction. I feel like we've gone over that well. All right. So the last category underneath the myotatic and stretch reflex are motor nerves, motor neuron types. Okay, so we have alpha and we have gamma, two types of motor neuron. These are motor, not sensory. These are the ones that stimulate contraction. Okay, alpha is really easy. It's the one that looks kind of like a fish, obviously. And whenever you think of a muscle contracting, the motor neuron that you're thinking of is an alpha motor neuron. If your teacher is saying, and then the motor nerve goes ahead and sends action potentials down to the muscle, he's talking about an alpha motor neuron. Most of the time, they don't bother saying alpha because they're so stinking common. That's really what, when you look at motor neurons, the vast majority of them are, that we talk about are alpha, okay? So gamma motor neurons are specifically little motor neurons that go down to the spindle cell, okay? And I have a dashed line representing that, and I'm going to draw it again right here so you can see it. And they go down to the spindle cells, which they're intrafusal cells and they're nuclear chain cells and bag cells, but they're made of muscle fibers, so they can contract. Now, when the gamma motor neuron comes down and tells the spindle cell to contract, it'll contract along with the rest of the muscle. Why would you do that? Okay, well, if your spindle cell didn't contract, okay, the rest of the muscle around it is getting shorter, okay? But if the spindle cell didn't get shorter itself, then the spindle cell would kind of look like this once everything around it contracted. So we'd have a really fat spindle cell while the rest of the muscle shortened, because it would just kind of, so the muscle is shortened now because it's contracted, but the spindle cell didn't contract, and so it kind of bulges out to the sides. And is it going to be able to detect a change in length if this gets stretched? Well, no, it wouldn't be able to do that very well. It would have to go back to its original shape where it's actually calibrated to sense change in its length first, which means that this muscle would be able to be stretched, clear out to normal, and then you would start getting sensory response from the spindle cell. The spindle cell has to be in its normal shape to function properly, and so it will contract along with the rest of the muscle, and the thing that does that job of keeping it in the proper shape are gamma motor neurons. My beautiful muscle, oh no. All right. And so alpha are the normal ones, and they go to extrafusal. Gamma are the special ones that go to the spindle cells to keep them the right shape to be able to detect changes in the muscle length. Okay? All right. So that is the myotatic stretch reflex. On, off, in order to save the muscle. The spindle cells are the ones that turn it on and off, and they have they are made of intrafusal cells, and then extrafusal cells are the rest. You have chain cells and bag cells are two types of cells inside that work together to give two types of information. Reporting to the brain for proprioception, like where are we? And then also is there unlicensed stretch going on? Wee wah, wee wah. Go ahead and contract, otherwise we're going to have a tragic accident. We don't like ambulances coming to our muscles. Okay, so, and then alpha and gamma motor neurons like we talked about. Moving on to the next reflex, inverse myotatic. Now that we've gone over all this, the rest of it is like almost the same thing. It's really cool because it doesn't take much more to understand this next topic, because inverse myotatic, the only difference is now we are talking about the tendons, which I'm going to go ahead and draw a tendon down here. Okay, now this section is a tendon. There's something called a Golgi tendon organ inside the tendon at the bottom, and it goes up here and has sensory, and it does the exact same thing. So I'm not going to draw it out. The only difference is if your tendon is the one that's going to break, you don't want to put more force on it on the same side. You want to relax it, and so it turns this off and the back one on. Okay? So the opposite one, I should say, because technically you could have it happen where the back tendon was the one that was going to break, and you know. So instead of on then off, it does off then on. And so it's the inverse or reverse of the myotatic response. And it's mediated by the Golgi tendon organ. All the motor nerves and neurons and everything are the same. There are interneurons between all of the sensory and motor neurons, because we already talked about the one exception that doesn't have an interneuron, and that's just in the myotatic response from the spindle cell back to flexing the muscle that the spindle cell is in. Okay? All the rest have interneurons. So, inverse myotatic, save the tendon. That's really it. So, the third reflex. You can go ahead and pause if you want and go over this without looking, and then we'll go on to the next one, or if you feel you still got room, we can go on to pain reflex. So, pain reflex is really myotatic plus inverse myotatic, okay? So, on the side where you have pain, if I stick my hand on a hot stove, I'm going to flex away from it. That flexion looks just like the myotatic response. It's triggered by pain receptors rather than a spindle cell, but besides that, it is the same thing, okay? Now, when I do that, I'm going to have a tendency to put my other hand out as part of the response. That's both for balance, and it would make sense if that was like, what if it was a saber-toothed tiger that was like biting your hand? You'd also want your other hand to reflexively shove it away. And so there are multiple things that it can help with. Balance is a big one, though. Okay? So, the side with the pain looks like myotatic. The other side looks like inverse myotatic. It actually is extending and doing the opposite thing. And so you have crossover in the spinal cord where, and all of the ones in the pain reflex have interneurons. You guys can't see this at all, can you? Okay. All right. So let's make this bigger. Okay. Sensory neurons come in, and they talk to interneurons. Those interneurons go ahead and do either negative stimulation of the thing that we want to relax, or positive stimulation of the thing that we want to contract. And this one, the one that does the positive stimulation, this is a detail. I doubt he's going to ask you this, but the cross extension part of this reflex, the crossover neuron, comes from the flexion interneuron. And then that goes to the other side of the spinal cord, which we are now making this whole circle here. This is all the spinal cord. And on this side of the spinal cord, you then have an interneuron. All right, I'm expanding the spinal cord again. I'm trying to make so you guys can see this. All right, you would have one going there, and then this branches and has another one going there. And then you would have, one of those would be positive, and the other one would be negative. So the positive one would be going to the opposite one. The positive signal, the excitatory signal, would be going to the opposite side of the muscle group. Okay, so this is what we call a contralateral response, because you have nerves crossing to the other side of the body. This side, my right hand is the one that was being mauled by a saber-toothed tiger. Oh no! And my left hand, when it has a response, that's a contralateral response because it's on the other side, the contrary side. Ipsilateral would be the same side. So ipsilaterally, I have flexion. Contralaterally, I have extension. And this is what that looks like in the spinal cord. I recommend you draw it out like once, maybe twice. But really, if you can remember why your body's doing what it's doing, then all of the neurons are really obvious, because it's like, oh, yeah, we want to turn this muscle on, so it's going to be a positive, excitatory synapse. All right, so that's everything for this. Myotatic / stretch, reflex, inverse myotatic, and then pain reflex. I hope that it helps, and if I can do anything to improve, I've heard about lighting, I'll work on that. Let me know, and let's rock it. Cheers.